In this video, we're going to continue our discussion of Taylor series. The question here is to find the Taylor series for f of x is equal to ln x at a equals 1. A equals 1 is the center of this Taylor series. That means we're going to evaluate the function and its derivatives at x equals 1. So sometimes we say x equals 1, sometimes we say a equals 1. We really mean the same thing. That's the center of the Taylor series approximation. So the key concept here is to find the derivatives of f of x and look for a pattern. So let's do that. We have f of x, that's the function, is equal to log x. Now differentiate, we get f prime of x is equal to 1 over x. Let's rewrite this as x to the power of minus 1, so it makes it easier to apply the power rule and find all the other derivatives. So f double prime of x, bring the power down, bring negative 1 down, and subtract 1 from the exponent. We get negative 1, x to the minus 2. The third derivative, f triple prime of x. We get minus 1 times minus 2. We get plus 2, x to the power of minus 3. Now let's find the fourth derivative, f4 of x. We get minus 3 times 2, so we get minus 3 times 2, x to the power of minus 4. Notice we don't write this as minus 6 because we're looking for a pattern. So now let's look at the fifth derivative, f5 of x. That's going to be minus 4 times minus 3. The negatives cancel out. So we get 4 times 3 times 2, x to the power of minus 5. So we begin to see a pattern. The nth derivative, fn of x, the nth derivative of the function evaluated at x, is equal to negative 1 to the power of n plus 1. This is what causes it to alternate, plus, minus, and times, and this part, clearly that's a factorial. Notice when the derivative is to the power of 5, we start at 4. That means we should use n minus 1 factorial. There it is. And the exponent is the same. The exponent of x is the same as the exponent of a derivative. So that's going to be x to the power of minus n. Now, if we plug the value of a equals 1, we get the nth derivative evaluated at a equals 1. That's going to give us negative 1 to the power of n plus 1 times n minus 1 factorial, and 1 to any power is just 1. So when differentiating, it's very important to keep f of x unsimplified, such as 3 times 2 times 1, so that we can find a pattern, so that we can see the pattern developing. Otherwise, it's going to be difficult to see what kind of pattern you're getting. So that's why we wrote this as 3 times 2, so later on we can see that as 3 factorial. All right, so what we have is f of 1 is equal to 0, f prime of 1 is equal to 1, f double prime of 1 is equal to minus 1, f triple prime of 1 is equal to 2 times 1, f fourth of 1 is equal to minus 3 factorial. And we can see where we got all of these numbers. We evaluated it right here. So f of x equals log x. That means f of 1 is log of 1, which is 0. F prime of 1 will be 1 over 1. That gives us 1. F double prime of 1 will be negative 1. F triple prime of 1 will be 2 times 1 to the power of minus 3. That's just 2. F fourth of 1 will be minus 3 factorial, and x is 1. 1 to any power is just 1. So there it is. And now let's look at the Taylor series formula. So we have f of x is equal to f of 1 plus f prime of 1 times x minus 1, f double prime of 1 times x minus 1 squared divided by 2 factorial, plus f triple prime of 1 times x minus 1 cubed divided by 3 factorial. Let's put these numbers in. We get f of x is equal to log of 1 is 0. That's f of 1. This part is 0. F prime of 1 is equal to 1 times x minus 1. F double prime of 1 is negative 1 times x minus 1 squared. Divide by 2 factorial. Let me just write this as minus 1. No need to write plus minus. And then plus f triple prime of 1, that's just going to be 2 times x minus 1 cubed. Divide by 3 factorial. And f fourth of 1 is going to be minus 3 factorial times x minus 1 to the fourth, divided by 4 factorial, plus, and so on. And the general term is going to be negative 1 to the power of n plus 1 times n minus 1 factorial times x minus 1 to the power of n divided by n factorial. So the Taylor series of the function log x at x equals 1 is equal to summation n equals 1 to infinity minus 1 to the power of n plus 1 times n minus 1 factorial times x minus 1 to the power of n divided by n factorial. Now we can simplify this because we can rewrite the denominator n factorial as n minus 1, as we can write it as n times n minus 1 factorial. And you can see how the n minus 1 factorial cancels out between the numerator and denominator. And we can simplify this as summation n equals 1 to infinity minus 1 to the power of n plus 1 times x minus 1 to the power of n divided by n. So this simplification is important. We rewrite the denominator n factorial as n times n minus 1 factorial, and then the n minus 1 factorial in the numerator cancels with the n minus 1 factorial in the denominator, leaving us with 1 over n. Alright, so we have the Taylor series of the function. That's f of x is equal to summation n equals 1 to infinity, fn of 1, the nth derivative of the function, evaluated at x equals 1, times x minus 1 to the power of n divided by n factorial. And we found the pattern for the nth derivative at x equals 1. This is negative 1 to the power of n plus 1 times n minus 1 factorial. So we put that in here, times x minus 1 to the power of n divided by n factorial. And then we did some simplification. And this is the most simplified compact form of the Taylor series of the function log x at x equals 1, which is summation n equals 1 to infinity, negative 1 to the power of n plus 1, times x minus 1 to the power of n divided by n. Now, we have found the Taylor series of the function f of x equals log x about the center a equals 1. Now that we have developed a pattern for the general term of the Taylor series, we're able to apply the ratio test to find the interval of convergence. So let's do that. We have limit n approaches infinity, absolute value of a sub n plus 1 divided by a sub n. This is equal to absolute value of negative 1 to the power of n plus 1 plus 1, we get n plus 2, times x minus 1 to the power of n plus 1, divided by n plus 1, all divided by a sub n, which is negative 1 to the power of n plus 1, times x minus 1 to the power of n, divided by n, and close the absolute value. Now, let's simplify that. We get limit n approaches infinity of absolute value of a sub n plus 1 divided by a sub n. This is equal to limit n approaches infinity, absolute value of negative 1 to the power of n plus 2 divided by negative 1 to the power of n plus 1 times n divided by n plus 1, doing some algebra, times x minus 1 to the power of n plus 1 divided by x minus 1 to the power of n, all inside the absolute value. So we get limit n approaches infinity, absolute value of negative 1, because we have the same base, subtract off the exponents, we get n plus 2 minus n plus 1, that gives us 1. Negative 1 to the power of 1 is equal to 1, times n divided by n plus 1. Now simplify this. We have the same base. The base is x minus 1. Subtract off the exponents. The n plus 1 minus n gives us 1. So we get x minus 1. Now absolute value of negative 1 is just plus 1. So we get limit n approaches infinity. N divided by n plus 1. We can remove this outside the absolute value because that's always positive. Times absolute value of x minus 1. Now, when we take the limit of n divided by n plus 1, recall we divide by the highest power in the denominator, which is n, and then take the limit, that's just going to give us 1. So the result is absolute value of x minus 1. By the ratio test, we make this less than 1, so the radius of convergence, r, is equal to 1. Let's find the interval of convergence. Let's remove the absolute value. We get x minus 1, less than 1, larger than negative 1. Now add 1 to everything, we get x, less than 1 plus 1 is 2, minus 1 plus 1 is 0. This is the interval of convergence, but the ratio test doesn't tell us what happens at the endpoints. So we have to check the endpoints separately. Let's check x equals 0 and x equals 2 separately. That means we have to plug them into the Taylor series and see what happens, whether the Taylor series converges at those endpoints or not. So let's look at the left endpoint. So f of x is equal to log x is equal to summation n equals 1 to infinity. This is a Taylor series of log x at x equals 1, evaluated with the center x equals 1, negative 1 to the power of n plus 1 times x minus 1 to the power of n divided by n. We're going to plug x equals 0 for x. So what do we get? We get summation n equals 1 to infinity minus 1 to the power of n plus 1. Plug 0 in, we get 0 minus 1 to the power of n. We get negative 1 to the power of n divided by n. Let's simplify this. We get summation n equals 1 to infinity. We have the same base, which is negative 1. Add up the exponents, n plus 1 plus n, and we get 2n plus 1. Now, it might seem like we have an alternating series, but in fact, we don't. So let's talk about it. We plugged x equals 0, and we obtained summation n equals 1 to infinity minus 1 to the power of 2n plus 1 divided by n. But negative 1 raised to an odd power is always negative. So we have summation n equals 1 to infinity minus 1 divided by n. Now negative 1 is a constant, passes through the summation, so we get minus summation n equals 1 to infinity 1 over n. But we know that summation 1 over n goes from 1 to infinity, is a divergent p-series. Divergent p-series with p equals 1. So negative 1 raised to the power of 2n plus 1 raised to an odd power is always going to be negative 1 for all n. And for that reason, this is not an altering series, it's just negative summation 1 over n. And we know that summation 1 over n is a divergent p-series. That means the sum actually goes to infinity. With a negative in the front, the sum will go to minus infinity. In any case, don't include x equals 0. Don't include, because the series diverges at x equals 0. Don't include x equals 0 for the interval of convergence. For the interval of convergence. Now let's plug x equals 2 into the Taylor series, summation n equals 1 to infinity minus 1 to the power of n plus 1 times x minus 1 to the power of n divided by n. We will get summation n equals 1 to infinity minus 1 to the power of n plus 1 times 2 minus 1 gives us 1, so we get 1 to the power of n divided by n. But 1 to the power of n is just going to be 1. So if we simplify this, we get summation n equals 1 to infinity minus 1 to the power of n plus 1 divided by n. Now we know that this is a convergent series, so it converges by the alternating series test. By alternating series test. Why does it converge? Because f of n equals 1 over n is a decreasing function of n, so that's decreasing function, and also the limit as n approaches infinity of 1 over n is equal to 0. And because it satisfies the conditions of the altering series test, this series converges at x equals 2. So basically, we include x equals 2 for the interval of convergence, but we exclude x equals 0. Recall at x equals 0, the series was a divergent p-series with p equals 1. So include x equals 2 for the interval convergence. F of x is equal to log x can be represented by the Taylor series summation n equals 1 to infinity negative 1 to the power of n plus 1 times x minus 1 to the power of n divided by n on the interval 0 to 2. Now, we don't include 0, but we include 2. So we include the right endpoint, but we exclude the left endpoint. So this is essentially the Taylor series of f of x equals ln x, and the only values of x for which this Taylor series represents the function f of x equals log x, the only values of x are in this interval. That means, for example, we can find f of 1.5 is equal to log of 1.5. We can simply plug in 1.5 for x and find a Taylor series representation of log of 1.5, but we can't do that if the value of x, for example, is 2.7, because that's outside the interval of convergence. So that's what the interval convergence means. It means all the values of x for which the Taylor series converges to the function ln x. So the key concept here is the ratio test does not tell us anything about the convergence at endpoints. So we had to plug in the endpoints manually, x equals 0 and x equals 2, into the Taylor series for f of x equals log x to determine the interval of convergence. And we found the interval convergence to be 0 and 2. So we excluded x equals 0, but we included x equals 2. And that's why we have a closed bracket on the right-hand side and we have an open bracket on the left-hand side. All right, thanks.